You know, it's one of those things we do 100 times a day without a second thought, flipping a light switch. But what's really happening in that instant? Well, it's the final tiny step in an absolutely mind-boggling journey that starts hundreds, sometimes thousands of kilometers away. And today, we're going to follow that journey from start to finish.
It really does feel like magic, doesn't it? Instant light. But it's not magic at all. It's this massive, perfectly coordinated system of physics and incredible engineering. So, we're going to trace that exact path electricity takes, from the very moment it's born at a power plant all the way to the outlet right there in your wall. So here's how we're going to break down this incredible trip. We'll start at the very beginning with the spark of generation. Then we'll hop on the high voltage highway to see how power travels so efficiently. After that, we'll look at how it navigates the grid, goes through the final transformation, and finally, how that power gets inside your walls. Let's get started. Our story begins right here at the power plant. This is the heart of the entire grid. Whether it's a giant hydroelectric dam, a nuclear reactor, or a coal-fired plant, this is ground zero, the powerful source for all the energy we depend on every single day. So deep inside these places, it all boils down to one simple thing: rotation. The goal is to get a giant turbine spinning, whether you use steam from boiling water or the sheer force of a river. That spinning turbine is hooked up to a generator, and inside that generator, a huge electromagnet spins inside massive coils of wire. And through this amazing principle called electromagnetic induction, that spinning motion gets converted into electrical energy. Right out of the gate, we're talking about a lot of juice, around 11,000 volts, sometimes even up to 25,000. Now that sounds like a ton of power, and it is. But believe it or not, it's nowhere near enough to send this electricity on a long-distance trip without losing most of it along the way. And that brings us to our next big challenge. Okay, so how in the world do you move this power across an entire country? Well, the number one enemy on this journey is resistance. Every single wire fights against the flow of electricity, and that fight wastes a ton of precious energy by turning it into useless heat. Now, the physics behind this is actually pretty fascinating. The amount of power you lose is equal to the current, that's the flow of electricity, squared, times the resistance of the wire. So since you can't really change the wire's resistance, the only variable you can really control is the current. And because it's squared, even a small drop in current leads to a huge drop in power loss. So the question becomes, how do you lower the current but still deliver the same amount of power?
The solution is, well, it's pure genius. See, power is just voltage times current. So if you want to deliver the same amount of power with less current, you have to crank up the voltage. And that's exactly what engineers do. They use what's called a step-up transformer right there at the power plant. They boost the voltage way, way up, which causes the current to drop way, way down. It's just an incredibly elegant fix to a really fundamental problem. And when I say they crank it up, I am not kidding. That initial 11,000 volts gets boosted to absolutely staggering levels. We're talking as high as 765,000 volts. This is our high voltage highway, and it's what lets electricity fly across hundreds of kilometers with almost no energy loss. Now, for the most part, our grid uses alternating current, or AC. And the big reason is that it's super easy to change its voltage up or down with simple transformers. But AC has this weird quirk called the skin effect, where the electricity tends to travel only on the outer surface of the wire, which increases resistance. For really, really long distances, like over 500 kilometers, it's actually better to use high voltage direct current, or HVDC. DC power uses the entire wire, so you get lower losses. The only catch? The converter stations you need to switch between AC and DC are ridiculously expensive. That's why we only use HVDC for these massive coast-to-coast electricity superhighways. So, we've got our super high voltage power ready to go. Now we need the actual physical stuff to carry it. This is the part of the grid we all recognize, those massive towers and power lines stretching all the way to the horizon. You've probably noticed that almost all of these big transmission lines are overhead. And the reason for that is pretty simple: cost. It is just so much cheaper and faster to string them up on towers. Sure, underground cables look way better and they're safe from storms, but the cost to bury them, and especially the time it takes to dig up a street to find and fix a problem, is just enormous. It only really makes sense in super dense cities. And for those few cables that are buried, insulation is absolutely everything. Think about it. You've got hundreds of thousands of volts running just a few feet under a busy sidewalk.
So they wrap the core wire in thick layers of materials like rubber or PVC to basically contain that immense electrical pressure and stop it from leaking out into the ground. Now, for the overhead lines, the real unsung heroes are the insulators. You've definitely seen them, those stacks of ceramic or glass discs hanging off the arms of the towers. Their only job is to stop all that high-voltage electricity from taking a disastrous short part down the metal tower to the ground. And the type they use tells you a lot about the voltage. Little pin-type ones are for lower voltages, but for our high-voltage highway, you need these long, dangling strings of suspension-type insulators to handle that incredible electrical pressure. Okay, our electricity has officially crossed the country, but we have a huge problem. That 765,000 volts would instantly vaporize your TV, your phone charger, pretty much any appliance you own. So the next phase of the journey is all about carefully and safely stepping that voltage back down. And this doesn't happen all at once. It's a staged process. At a big regional substation, that 765 kV gets dropped to something like 132 kV. As it gets closer to a city, another substation knocks it down to about 11 kV to run along the main roads. And then finally, right in your neighborhood, one last transformer brings it down to the safe, usable 230 volts for your home. That last step happens inside that familiar gray barrel on a utility pole, or maybe a green metal box on the sidewalk. Inside that box, you've got a steel core that guides the magnetic field and copper windings that do the actual magic of turning 11,000 volts into 230. The whole thing is sitting in a bath of mineral oil to keep it cool, and those porcelain knobs you see on the outside, those are called bushings, and they're just safe insulated connection points for the wires. We are on the home stretch now. The power has traveled hundreds of kilometers, it's been transformed multiple times, and now it's just a few meters away from completing its journey and entering your home. A service line carries that nice, safe 230-volt power from the transformer to the side of your house. The very first thing it does is pass through your electricity meter. That's how the power company knows how much to bill you. From there, it goes into your breaker panel. This is like the command center for your home's wiring. It splits the main power feed into all the different circuits for your kitchen, your bedroom, your lights, each one protected by its own breaker, sending power through the walls to every single outlet and switch. So when you zoom out and look at the whole system, you realize every single step in this journey has a critical purpose. Sending power at super high voltage is all about efficiency. It saves energy and keeps our bills lower. The whole step-down process is all about safety, making sure that power is usable in our homes. The massive, interconnected grid gives us reliability. And those last few components in your house, like breakers, are all about protection. It's this beautiful, complex dance designed for one simple thing, to deliver power to you safely and affordably. But here's the thing to think about. This entire incredible system was designed for a 20th century world, a world with a few giant power plants sending electricity out in one direction. But what happens when power starts coming from everywhere? From millions of solar panels on rooftops, from local wind farms? How does this amazing journey change when it suddenly becomes a two-way street? Well, that is the huge challenge